My talk is about AI-enabled robots. It's about bringing together automation, digital technology, machine learning, AI, towards creating machines that are able to learn, to self-improve, and don't have to be programmed in a classical way anymore. So it's kind of the next step of automation, the next step of intelligent machines that have come to reality. So I will try to give you an overview of where we are in the real world and what is really possible. So not only in lab environments, but what can really tremendously change what we call nowadays Industry 4.0, and where can we be in the next couple of years. So I think we've come a major step forward beginning in the 50s with the classical industrial robots that have done certain automation tasks. They were done by means of hydraulics technology. They were huge positioning machines. Towards the 80s, where we had the first programmable machines that could be programmed to do certain automation motion tasks. However, these machines cannot interact. They just know where they are. They can move very accurately in space. And this has led to the huge industrial revolution in the 80s and 90s regarding the industrial robotics technology. So these massive machines that are behind safety fences, so they are heavy-duty machines, they can position certain parts, they are behind safety fences, they cannot interact with humans, so they would be dangerous to all of you. And why? Because they are lacking a very distinct sense. We have 5 senses, some argue even more, but the most important one, presumably, is the sense of touch. And why is that? The sense of touch enables us to interact with the world. It enables us to be intelligent in the world, to interact with it, with the complex physics that we all have to face every day. And the machines you just see here on this slide are really everything but not intelligent machines. They are pure positioning machines. And interestingly, if you think about the application domains where they are used most of the time, which is automobile manufacturing, the maximum automation degree in these factories is approximately 20%. So you would have probably guessed there's much more of these robots being used, and this is due to the fact that they don't feel, they cannot interact, they cannot physically interact with the world. It's actually just a couple of 100,000 robots being sold every year as of today of these machines. And what do they do every day? They do spot welding and painting. That's the 2 major applications that these industrial robots can do. And obviously, this means that there is a certain limit towards automation, what is possible and what is not possible. And because we cannot automate all the things that are very delicate, that need our hand, that need our use of tools, there is a huge range of applications, in particular in assembly, which is the other 80% of the applications in the automobile manufacturing space, and obviously all the applications that we see in small and medium enterprises that could not be automated, that could not be, to a certain degree, digitalized or automated with state-of-the-art automation. And obviously, due to that fact, and this is probably the purest fact why most of the productions of electronics manufacturing has moved from Europe and the US and Japan towards countries such as China and so on, to the developing countries. Why? Because the sense of touch that makes all of you so distinct, humans, it makes us humans to a certain extent, is something that we could not automate, that we could not embed into these robots. And in particular, we could just do it to a certain extent in lab spaces, but not in the real world. And due to that fact, this massive use of low income labor is being used in countries such as China and so on, in order to manufacture all the smart devices and all the cameras that are doing the photos that we just have in this room. And this is to a large extent work that is laborious, that is possibly dangerous, it's extremely dull. It's something that people in Europe, in Germany, would probably not do. And obviously this is also a very big drawback for the industry we have here in Europe. Why? Because the large body of small and medium enterprises that we have in Europe, just alone in Germany, we have more than 20,000 small and medium enterprises, simply have no access to automation technology that could make them compete with these global players that outsource all the manufacturing towards countries such as China. And obviously, due to the increase of demands, there's more and more of this cheap labor being used and becoming necessary, especially also in the design space of clothing and so on and so forth. So electronics, clothing, this is really where the sense of touch is extremely important. It could not be automated at all, and this creates obviously huge ethical problems that we all see nowadays, and we all know of the problems we have in these manufacturing sites. Luckily, Here in Munich, here in Germany, we are working towards new applications in robotics. We try to develop new devices that solve that issue. And I think what is really important is, if we take a step back, is that humans have always been wonderful in creating new tools that are able to make our lives easier. So I really and truly believe that robotics is something that we should call a tool. It's a tool for all of us humans. The robots that we develop are called human-centered robots. We use them as this flexible box of tools. It's similar to a stone wedge or the PC or the internet. We use it as something in our everyday life to make things easier. And this is something that will make it possible to essentially free us from the work that is really dangerous, laborious, and in a sense, it's slave work. And I want to give you a kind of short impression of the technology that we've been developing and show you something that really bridges the gap in real world, not only in first applications in the lab, between industry, learning, and assembly. So we will show you an application and demonstration of how we actually embed learning into these machines and not simply program them with expert knowledge. So it's the intelligence via AI technologies that makes it possible for these robots to become intelligent and to become a smart tool. Okay, let me show you what these robots really can do. And we would show you kind of the basic technology behind it. So this is a new robot that we've been developing. It's purely made in Germany, so it's also being manufactured in Germany. So let us show what, as classical robots, it can move very fast, right? So it's something that all these robots have to do. They need to be fast, dexterous, they have to be very precise. So this is something that obviously we all need for industry. However, what we also want is that these robots are safe for humans. So we want that this robot moves, and if something goes into the way, the robot understands that there is something. So I touch it, it feels it. It has a sense of touch, it safely interacts with me. I interact just via physically touching the robot, giving it a nod, and it understands that this was something it was not supposed to do. And the most important thing maybe is also that this robot cannot only move, but it kind of mimics the way that humans move, that humans are able to modify their muscle tensions. So we basically have kind of what we call virtual muscles. So the robot is really now stiffening up. It's kind of pre-tensioning the virtual muscles in its, let's call it central nervous system, right? Let's call it the central nervous system. And it's stiffening up. It's a very stiff robot now. But it can also be a very compliant robot. So as we see now, the robot is now becoming compliant, right? So now it's a very compliant robot. It's like a little baby or a child that I just told, hey, don't stiffen up so much, come on, follow me, right? And this is kind of the basic technology, embedding this kind of sensory motor skills into the robot and being able to do things that robots could not be doing before. The other thing that this system can then do is be very accurate in regulating forces. So if you want to do screwing, if you want to do assembly, you need to be very sensitive and you need to understand how to basically contact and be very, very accurate. Okay, can we redo? Redo. Can you restart this one? Okay, now? So I tell the robot to really push with exactly 1 kilogram on this thing. And just with its internal sensory knowledge, without looking, it's 96, it's almost exactly 100. Without looking. So this is sense of touch, right? And if we now go further, so with these basic technologies, the question is now, if we have robots that can feel, that can interact, how can we actually make these systems be very compliant and learn? So can we do things that could not be done before? So for example, I was saying assembly is a problem in robotics, right? So these robots cannot do assembly. So let's see whether this robot can actually do certain things that could not be automated before.
Hi Sami, my name is Franca, and I want to show you a secret. Can you please give me the key?
Okay, sure, let's do that. And by the way, I have no devices here, right? I just interact with the robot via touching it and just holding here. The robot feels that I touched it, and now is doing something that other robots could not do, right? Similar to a child, it's basically taking the key, opening this small box via its sense of touch. It doesn't see, it's a blind robot. We intentionally made it blind here, and it just opens that drawer very delicately, very sensitively. It uses the sense of touch we just saw. It opens the drawer and wants to show me something. It's the black box, exactly. And there's something in the black box, but I don't want Franka to show us now. Close it, exactly. So in the end, we're going to relieve and show the magic that is in there. All right, so obviously this is something that usually you would program. In standard applications, in order to do this, just to give you a grounding, this takes months to program it by an expert. And what I'm going to show you now is that on stage, live, this robot is going to come to life and basically learn what we just saw within a couple of minutes. So
all right, here is the key. Okay, then let's start at the beginning. I am erasing my memory.
All right, so Franka, the robot, is now basically pre-born, right? So now let's wake up Franka and teach it, like a little child, step by step, to be able in the end to open the box. So think, all the ones of you who have children probably understand what I'm talking about, right? It's becoming a 3-year-old child, essentially, within a couple of minutes. So let's wake Franka up. It's booting. And as you all know, if there comes a newborn, they are not able to hold their head, right? They're not able to hold their hands. So let's see whether this robot is actually able to hold itself, to stand and balance. So let's activate. It doesn't know what gravity is. It doesn't know how to fight against gravity. It's falling down, right? Think about infants that try to hold up their head. This is something they have to learn over many iterations. So let's activate this learning program. So these are now AI technologies that bridge the gap, similar to humans, how to learn yourself, to learn what a body really is. And I just tell the robot by putting him here, start.
I want to learn about myself and the world.
Okay. So Franka is now moving around. Think about how infants do it. They do what we call motor bubbling. Right? It's involuntary motions of infants. If you think about them, they just move around. They try to get a relation between their body, to learn the body schema, to understand if you activate a muscle, what motion do I generate? And this is exactly what you see here. Franka is generating involuntary motions, just arbitrary ones, and understanding if I move my virtual muscles like that, this is the motion that I become. And this gives it a kind of introspection into its own body, and now kind of finished, just took a couple of seconds. So let's see whether Franka can actually hold itself. Oh, it already did. It didn't fall down anymore. So now Franka really has an understanding of what does it mean, like a 2-3-year-old child, to hold your own arm. And what can you do with these things? So obviously, as you all probably understand, we now let Franka do something. So as all robots, you know, they can do pick and place, right? So they all want to grab something and place it somewhere. So maybe like a 1-year-old.
I can now stand up. Let me show you what I can do.
So picking up something and placing it somewhere. That's something that I guess all of you know, but without programming, right? This is now something that Franka learns because it knows its own body.
I want to learn something challenging. Give me that key, please.
That sounds clear, right? So now, how can we basically use this knowledge of knowing your own body, moving towards a new skill? Okay. Here is a small hole, and maybe we can zoom here. This is a keyhole, and I want that Franka learns that keyhole. This is a very challenging task. If you think about children, they have to be about 3 years old. 3 years of learning of humans to actually insert that. So let's try. Same game as before. Do it from the side. Oops, sorry. Take it. Okay, and now Franca is actually learning how to insert the key in here, blindly. So it's trying it. It's a very challenging task. And similar to a human child, this seems to be something that is obviously very hard to be done, right? I mean, there is no programming, it just has learning algorithms, so AI technology embodied into this system to actually be able to try to self-improve. So I didn't type anything, right? And this is actually happening here online. So I'm not having pre-recordings here. And it's trying to do this and it seems hard.
That was too complicated. Let me try something simpler.
Okay, makes sense, right? Like little children, if you just have a newborn that just knows how to move, it cannot just insert a key, right? Okay, let's change that. Let's try something more easy. So this is what we call the peg-and-hole problem. It's a very simple geometry. It's actually something that for industry is extremely relevant. It's something that you have to assemble. It's 1/10 of a millimeter of accuracy, below actually. And here is the hole, and we try to basically use that knowledge, create it, and do the same thing as before. Franca now learns how to insert into this hole. And the big question is now, can we actually create knowledge? Can we create something that is more than just imitation by mimicking how humans learn? So the robot is now successful, right? It's a bit simpler problem. It's doing the same thing as before. And the big question is now, obviously, if I learn this hole, can I generalize to this keyhole? This would be real knowledge for the first time being generated. So this is not just imitation, doing something that humans do, it's creating something that is of more value. And that's the big question. And the nice thing is actually, what you see here is not being computed via humongously large deep networks. It's a very clever AI technology that makes use of looking much closer at humans. How do humans learn? How do humans move? How do we use our hand? It's a marvelous tool. It's the most complex tool that has been designed by evolution, and we basically mimic the way that humans do it. And just to be very clear on what this means, you all see this little other black box here, maybe? And this is the computer on which the AI technology you're seeing here, running online, actually works. It's a standard small computer on which human bio-inspired AI technology basically works to make this robot smart, as you see it. And it doesn't take hundreds of thousands of iterations or humongously large data centers that are in the cloud. It just takes a small standard PC if you do it the way to understand the human. And this is what I call the art of manipulation. Obviously, this is something that Franca has to do over certain iterations, and you see it gets a bit better, and sometimes it fails. So we call this the balance between exploitation and exploration. And the nice thing is that if you look at how humans do this, the robot seems to create something that is of more value than the pure imitation and programming of things. So the question is, how do you then do the transfer to other tasks? And this is now approximately maybe 25, 30 trials. You see it's really human-like. It tries to wiggle in. It's really doing this with a sense of touch, with a change of motor controls. And it's actually extremely sensitive in doing these tasks. Okay, just probably a couple of more retries. And then at some point, Franca will say, okay, I'm done. I cannot get any better, right? You see how it gets faster and better and better? So it's true learning here on stage. So a new strategy that doesn't turn out to be that great. Okay,
I think I got it. I want to try the key again.
wonderful. All right, so Franka acquired some knowledge. It now says, okay, I think I'm confident. So now let's see. The big question, if you look at these two objects, maybe a bit closer, they are totally different, right? Just visually. And if you think that this knowledge could be used for solving that issue, that would be a wonderful thing to have, right? Let's see whether Franka is successful. Again, now we basically use the same knowledge that was just created and works. So this is actually the first time that a robot was able to actually learn motor skills similar to humans and transfer it to a totally different problem. And now obviously this knowledge can be generalized and improved again. And now let's go even one step further. The big question is, okay, we've got this basic knowledge from the pack. We have the transfer, which we call interclass learning, so between classes. We transferred that knowledge to that particular key. And now, can we actually transfer it to the final problem we just saw before, right? So can we now finally open the black box?
That was fun. Can you please give me the other key?
Okay, the only thing that Franka knows in this example is obviously where roughly the box is, right? We could do it with computer vision as well. But now the same knowledge is being used. Let's see whether we're successful. And now let's see what Franka wants to show us.
Look, this is what I want to be as a grown-up robot.
So let's say Franka is now 3 years old. Let's see what Franka wants to become if she's a big robot. A humanoid. It wants to become a humanoid. And maybe for next DLD, we see what Franka really wants to do, and maybe we can switch back to my final slide. And I think this exactly shows what these robots will do in the future. So Franka, you want to basically become a little helper humanoid for elderly people. Is that right? Okay. I love the idea, and I'm going to help you to create that. So we just saw the first steps towards true AI-based robotics, learning robots that can acquire skills similar to humans. And I think we're really on the way towards this grand vision. Thanks a lot for having me here. Thanks, Steffi, for creating this wonderful DLD.